So folks, as you saw earlier, we compiled the Quartus program for this project, and we created the RBF file. Then we copied that RBF file and tried to reboot, but it did not reboot. And what I am getting is basically the application terminated message over here. In the first attempt, I did saw something related to the MAC address. Yeah, warning, failed to set MAC address. So this kind of helped me focus on the Ethernet. I feel that maybe there's additional peripheral in there that I don't need for this 00 mselect configuration. So what I want to do is remove this Ethernet and then give it another try. But before I do that, I actually look back at my earlier attempts, and the last attempt that I made did give me a hint that I did not use the Ethernet connection either. The eNet was present but was not used. So when I tried to look up any one of these parameters from the eNet, except the text TX enable, or oh yeah, init n, except this init n, all the others are not linked, and so that's a pretty clear indication that I need to remove this eNet. So I have my designer open, and I removed the eNet, Ethernet Media Access Controller, and I did finish. It did not ask me to generate, so let me try it again. I want to generate this template, this component template. So this component template and the port mapping for the component. So before I do that, I want to compare my configuration against the designer configuration and make sure that all the names match. Okay, so let's get the template, instantiation template, and now I see, let's compare it against the good working example I have. And nice and clean. Let's see if I can bring it up on top of this. Okay. Essentially here, component SDIO, USB 1, SPIM, GPIO, and yeah, UART. So yeah, we are okay. No eNet in there. Okay. Generate HDL. Generate. These are same warnings. Nothing to be concerned about here. Alright folks, so HDL is generated. This updates all the file. I'll take the instantiation template, copy it over, and essentially what I'll do is I will just make sure that my names are, yeah, let's do a little shortcut here. I don't want this video to take too long. If I have to come around, then I'll come around and redo this. But I feel, yeah, they're all here, other than the Emacs. So I will disable this instead of trying to copy it over, then rebuild. Just disable the piece that is associated to the Ethernet, and I have a clock reset and is present. Clock is present. Lightweight out export name is still the same, so I don't see any change in there. Okay, and this Ethernet portion, let's see which one we want to keep. This should be present here in the GPIO section. Ethernet and net N actually, and then the rest should be disabled. Ethernet and net N. Comment that out. Just keep that in. Saved. And we will recompile. The pin is changed. Okay, I'll follow the same steps and thesis, then we'll go to the full compilation. Okay, so synthesis is complete. Let's check our pin map. Does it still contain, I want to make sure that it still contains Ethernet pins or not. I don't see it in there, which is good. This is a good sign. Okay. Now that we have removed Ethernet, I believe we have to rerun the TCL scripts. And then once we run TCL scripts, then we can run our full compilation. So let's run this one more time. Assignments complete. Seems like it's going okay. Looks like it. Come on, come on. Okay, successful. Same thing, parameters and assignments only. I want to make sure that that these scripts are executed. Okay, that is complete as well. And now we will initiate the full compilation. And I'll come back to this once the compilation is complete. Alright, finally, this is completed. Compilation is done. Next, we will convert the SOF file to the RBF, raw binary file. Everything else remains the same. Output, output is fine. This is okay. I believe it's putting it out in the same directory. Yeah, that's fine. That's fine. We don't need to worry about that. So SOF file, I need to, let's see, it's in output. Yeah. And yes, and we will generated. Let's close this and come back to, let's say we have generated that. So now we need to come back to our main file. Let me see if I can pull up our. Alright, so we have an SD card. Let me see if I can plug in my camera. So we have our SD card, and I will plug this in. Now our project is this CG4 test 2. Output file RBF is right here. Let's open a new tab so we can see what I am doing here. So if you if I've included the video, so I've already backed up the original RBF that came with this image in this folder. I keep it in case my RBF does not work. I can pull it back and make sure that that Linux is fine, HPS is loading okay. So we need to make sure that this output file is named exactly as this SOC system file name. So I will copy it and remove it and rename this guy. Alright, all we need to do is boot this up and watch our UART session. So UART is ready. The eject didn't happen, I believe. It oh, okay. Seems like it is ejecting or not ejecting. Okay. Alright, so I'm going to remove it and load it in. MCell is set to all ones. See if my view is better. Okay. I have so much mess here. Trying to work on another project at the same time. Seems like it loaded, but it is not sure what to load. MAC address is still failing. But at this time, it seems like the FPGA loaded. Let me restart again. Initial code loaded. First light is on, but my kernel is not loading now. And if I change it to, it shouldn't take that long, so I'm not going to wait for it to complete. I'm going to switch our configuration to 32, and let's see what our kernel does now. It says application terminated right here. Okay, there's something else I need to fix then. Let's come back to this once I figure this out. Okay, folks, so finally this is in working condition. Okay, folks, finally this HPS booted up, and I see the problem now. So in my project, I was making two different mistakes. First one is that I'm executing too many TCL scripts. So in my project, when I get to my TCL script portion, I was executing. There were two different groups: the SOC script, SOC system script, and then there was a DBL, which is created when I run the synthesis. So for synthesis and the this option, analysis and synthesis option, when I run this, it creates this DB folder, and it has its own scripts. Essentially, this action creates a separate TCL script folder, and the compilation creates its own TCL script portion. So, or the folder, I should say. So, essentially, what I need to do, because the final compiled file is the one that goes to the board, I should only compile the TCL scripts that are connected to the main compilation. Now, how do I know that? Which one is the main compilation folder? Is through this. You see this SOC system synthesis submodule, and it tells me that it's looking for this path, the files in this path, and when I go to my TCL scripts portion and I see this SOC synthesis submodules, I should only run these two files, and that's it. Not these two, just these, the one that are connected to the project. These are not connected to the project. You can see that they are in a separate tree. They are underneath, I believe they are underneath SOC system. No, they're underneath the project, but they are not underneath the SOC system. This is how it should be structured. It should show in your script window as structured, and if it's not showing in a structured format, then it is not going to complete the physical connections that the HPS needs to connect to their FPGA. So this is one big point you want to keep to your future project, and I'll keep to myself for my future projects. Okay, another view from my second project that I compiled for bidirectional testing, and this is a successful project as well. And this one is much more cleaner because I did not use the synthesis or analysis at all. What I do is compile the first time, complete the compilation, then come back, run the TCL scripts, and then go back compile again. It takes longer, yes, um, but I don't see any other um, associated folders that might confuse me. So this is much more cleaner. Just FYI, I wanted to bring this to your attention. Now, okay, so this is TCL script. Another piece that I was making mistake on was the addition of the SOC system file. So earlier I mentioned that I was using the, let me see here. I was using the SOC system, the QSys design file, which did work in one of my tests, and it happens to be fine. But however, for this project, it did not work. So I came back to the QIP, and when I did that, I started noticing in my hierarchy that my main file did show a hierarchy, but did not actually show me anything under the hierarchy. So when I tried to open the hierarchy level, there was nothing underneath. Now you do see SOC system because I've successfully ran the compilation twice. TCL scripts are executed as well, and only the submodules ones are executed, and that successfully created this hierarchy, and everything else is connected and show up just as my other test projects. So I feel that these are the two main points that you want to keep in mind when you want to compile your site, compile your project, and you want to make sure that these two things um, are showing up as I stated. So okay, so that's one. And now if you want to, now let me recreate that. I think if I recreate it, you probably will see exactly what I mean by that. So what I will do, I'll go back to my projects, to my test2 project, and let me bring it up to my right. And you see there's a DB folder. Now this DB is not showing up in my TCL scripts anymore. So I don't think I need to delete anything. So what I will do is remove my QIP. Remove from the project, and I will run it without the QIP, and then it will say that, hey, you're missing so many things. You might need to add some additional, and I will come back here as well. Let's go back to the designer, all the way back to the designer, and let me show you from that what you should see, what you should not, and this will be a good flashback, and we can compare our current project, or not compare, but we can at least revise exactly what peripherals are in this project, and what connections are made. And while I have it open, I realized there was another thing that I did in this project that was different from the earlier attempt, and I corrected that as well. So we are in our QSys design, and this is one additional piece. The reset that is showing up in the components was basically because this. If I if I connect the reset, clock and reset to the HPS reset, then that does not show up, which is basically, let's see if I can move these together in one view. And I think I removed it, yeah. So, which was this reset that was earlier showing up in my components. After making this connection, it disappeared. So I believe that it was this guy, clock and reset, although the name is different, but it disappeared after this. So I assume that this is why it's not there anymore. Okay, so let's go over the peripherals one more time. So you know, and you can compare this against your project. The HPS peripherals, no Ethernet, no NAND, no quad SPI, SDMMC, yes, 4-bit data, the USB controller, yes, but USB 1 only, and SPI, SPI M1 pin, and then the mode, and that's it. Nothing in the SPI. Then UART 0 included, and that's it. So that is basically the peripherals. No change here. Peripherals are still the same. In the last attempt, I removed the Ethernet, and I keep it removed. No need to use it in the FPGA. Okay, and all I did then is I generate my HDL, which is basically going to create all those SoC system components. And let's generate it. One thing I noticed when I was browsing in my folder, in my project folder, I noticed that after running this generate, it creates a SoC system handoff. And it has the C++ files or C files that I think I can use in my project. I haven't used them, but basically they can give us a good idea of which addresses are available to us. So let's see, let's open just one while this is executing, and let me bring it over here. And as we can see that references to the base address, let's maximize it so we can see the exact format. And it's using SDRAM H. SDRAM H is up here somewhere. SDRAM IO is here, but SDRAM H I do not see in my folder anywhere. I don't think so. Okay, no problem, no problem. This is fine. I'm not using this, but this may help you. So I thought I should point out in this project, what I will do is I will use our base address of this Avalon memory. Once it's complete, I'll get to that. So this conduit where this external connection is being made, the base address will be our connection point to read the memory from the FPGA. Sorry, not from the FPGA, sorry, to read the memory from the HPS. So let's allow it to complete first. And come on, come on, come on. Maybe if I stop my video recording, it will give it will release some resources and it may complete quicker. Usually it happens when as soon as I start thinking maybe I should stop the video, it completes its compilation. So, all right, that's good. Close this and let's look at our base address I was referring to. The base address is this right here, 0. 0 is our base address, and we are only going to read the first 4 bits, which is this F. So this is good. This is good. I don't think we need to discuss any more of this. We have discussed this plenty in our sections in other sections. So let's continue. We generate the HDL. Now what we do is we take the instantiation template, basically copy this whole section, gives us the components and the connection point for the components, the port connections for the components. And we come back to our project. I did already copy it over, so just to revise and rehearse the same thing over, Control V. And we take our component, just the component, the rest should be the same. If it's not, it will tell us. So I'm taking just the component and I'm putting the rest in the comments. So it's not going to bother our project. And I'm going to copy paste over our component declaration here. And this time what I'm going to do is add our QIP file. The quip file, yeah. I think it is in SOC synthesis. Yeah, there it is. It's very imperative remember where your TCL scripts, the one that you execute, you have to remember the path of those scripts and you have to pick the quip file from that location. So in case if your synthesis and analysis, they create an alternate folder, it might confuse your system. So yeah, that's just wanted to give you a heads up there. And make sure your main VHDL is up at the top. Apply and OK over here. Another thing we want to do, we want to make sure that it's top level entity. So we'll come back here. Oh, it's taking awfully long time. I don't get why. I have plenty of resources available in my system. Anyway, so I'll come back here, right click and set this as my top level entity, because this is where the compilation will start, and then the compiler will go to the quip file and then all the associated files that it needs. Okay, so let's come back to the hierarchy, and as soon as I connect and I didn't ran the TCL scripts yet. So as soon as I rearrange, make this a top level entity, the hierarchy should show up just like this. And what we will do, I'll follow that same pattern, although I've already ran the TCL scripts. What I'll do, I'll start compile and then run the TCL scripts and then come back and rerun the compilation again. So I'll run the compiler twice, basically twice. So I'll do this for our video. The first time, if you haven't run the TCL scripts like myself, or somehow through synthesis and you've ran the TCL script successfully, the first time it should give you some error messages. It will not give us now because I've already done it twice. The project probably have some resolved connections that it will not complain about anymore, but first time it did complain, and it did say the program is just too large, you should switch to a different FPGA board and so on. So but yeah, that's not the case. We know our program is very tiny. So it's compiling, and I think this should complete in a few minutes. Maybe I should come back. Okay, it's staying at 23%. Yeah. All right, I'll stop the recording here and I'll come back when it's done at 100%. and we will run the TCL scripts. Okay, folks, so now the compilation is complete. And what we need to do is rerun the scripts. Or in my case, I'm rerunning, but for you, it will be the first attempt after the first compilation. So run the script, number 1, parameters, number 2, assignments, pin assignments, and that should complete the connections. And in your case, what I want you to do is look at your pin planner and make sure any pins that you haven't assigned, that you created for your code and not for the components, they are present and they have the right pin assignment. The rest should just be there. For example, the DDR, the let's widen this a little bit, the I2C and all this USB all the way up to here, they should be left alone. Only the ones that that you will connect into your program. And I do want to emphasize on the 50 megahertz clock. Make sure that you connect that yourself. I'm not sure if the fitter assigns it correctly, although it does show now. It is assigning the same pin as I did. So maybe you can leave it and try execute the compiler and see if this connects to the right fitter location or the pin location, and cross-check against your manual. And I believe there are 3 different connection pins that you can use for the 50 megahertz clock, and it depends which one you want to choose. And I've chosen the first one. Coming down here, as you know, that we're using LED pins, then we are using motor pins, and then switch connections, and that's it. So we have already connected those in the earlier attempts, so I'm going to leave it as is, and we ran the TCL scripts, and now we will execute the compiler one more time to make sure the TCL script, the files or any connections that it generated, that the compiler takes up the fresh ones, the fresh files, and reconnect them to the rest of the project. Alright, I will stop it here again, and then we'll come back once it's complete to 100%. Alright folks, so finally the compilation is complete, and now what we will do is we will convert the SOF file into RBF. So let's change the programming file type, output file RBF. I'm not going to disturb that. SOF data, and we will specify our SOF file. Oh, now in sequencer, going in the wrong place again. Output, there you are, and we just generate. And as soon as it generates, I'm going to copy this over into my SD card. Let me see if I can plug it in. Generated successfully. All right. SOC system. Oh, it was in the output files. Oh no, SOC system synthesis. Synthesis RBF, there it is, 1148. So we'll take that. This is our fat partition on that SD card. Copy it here. Remove this and rename our newer to the SOC system. Then I'll do safely eject. Trying to go a little quicker because I feel that I should do this quickly. Apologize if I'm going a bit too quick. Give me some comments, some input, so I can in the next video I can slow down and figure out a much better method to explain as I'm executing. So okay, now I will remove my SD card and let's turn on our camera. Okay, SD card going in. Let's see what happens here. The M-cell switch is already switched to, let me see if I can zoom in. All on at this point. As you can see, all the switches are in on position. And let me zoom out. Okay, that's a good view. Okay, power on. Where's my boot console? Here's my boot console. You can see the HPS booted successfully. So essentially that was basically it. The light is blinking, so when I plug in the power to my motor, you will see that it starts moving again. Or for me it's again because this is my second attempt in recording this video. Alright, so yeah, that's that. Let me throw my messy area. Okay, so this is currently hooked up to the same output as from the switches, so I can slow it down. I left that logic in place to make sure my in case if my HPS portion freezes up and my whole FPGA stops executing for some unknown reason, for any unknown reason, I would basically use this output pin to figure out the current execute state. So clearly this is executing and motor is turning fine, no issue there. So what we can do is now move into our next step, and my video has frozen again. Yeah, it's back again. Okay. So basically what I meant to say that that pin and that logic is left in place to basically debug, or not debug, but to validate the working condition or working state of my code. So the code is executing, everything's fine. Now we can move to the next step, which is going to be our HPS programming. And I'm going to stop this video and prepare for the next one. Okay folks, so now we will start working towards the HPS portion of this project. So our FPGA is configured. It is controlling the motor, and through the LED pins 1 and 2 we can see the status of that motor control. So as you can see, so that portion is working fine. Now for the HPS side, we have to configure a C++ program that will write to the memory location. And which memory location? We will, let me see if we can program, let me see if we can open this designer, and we have to go back to that designer to figure out this this memory address. In our case right now, we're just reading, the FPGA side is just reading from that memory location, and it's just one memory location at this time. So the place where this HPS is going to write to is going to be 0, the initial, and the very initial address of the memory location. So, oh, it's right there. So this is our, if you remember, if we go back to our PIO, and our base memory address here starts from the 0 and goes all the way to F. And so what the HPS is going to do is going to write to the 0 with the length, or the, we could say, width of the 15 bits. And it's just going to write it there, and FPGA is already reading from that location. So once the HPS writes, we will increment, let's say after every 5 seconds or every 2 seconds, we will increment that to the next number and the next number all the way up to 15 and then back to 0. So that's what the program is going to do, and that will tell us exactly the working state, or it will basically it will validate the working state of the read and write process through this lightweight memory location. So let's close our Quartus. We don't need this anymore, at least for the read portion. We'll come back to this when we want to write from the FPGA, which is going to be the similar process. Instead of output, we will say input, and then we will have to decide the width of the number of bits that we need to occupy in the write sequence. And then similarly, we'll modify in the HPS to modify for the read portion of the HPS, from the HPS. So what I will do again is open the NetBeans. We did configure the NetBeans configuration before. However, now that we changed the IP address from the static to DHCP, and we installed a few things, I don't know if we changed it back. I don't remember right now, so let me see if this is back to, it's configured for 10, and I think I did make that connection. Okay, yeah, it's there. As you can see, 168.40.10, 168.40.10. Now, at least what we will do, and automatically connected. You can see this green, the TV icon is green right now, so that means that it is connected. And when I expand my connection, you'll see this, the tool chain and the compiler that it detects. It's there. So that means that our connection is good. Now, did I create a project? Nano MEM test. This project seems to have created, but I don't see that now. Maybe this is before. Maybe this is before. So it should be in home root Nano MEM. So if I browse in the services, I should be able to browse. Let me see. Yeah, could not load. So it does not see that in there, and now it disappeared. So it's probably uh, from the time when I was recording, making the um, test recording for the first time, when all my recording was corrupted, and I had to restart, and that might have been from that time. So what I will do is recreate a new project. I will say new C++ project, and it is a application, and you'll see that this is in home root NetBeans project. I think it will create a folder. So nano, I'll say HPS this time, HPS test, and this is good. Say finish. Go back to our projects, and sources, and our main CPP is all good. I do want to browse my not sure if I can. Home folder is not supported on the system. Okay. If I do I don't want to path map right now. Okay, maybe right now I don't. I can skip this for now. Let's make sure one more time here. Expanding the project does tell me that the project folder is created, but the location through the NetBeans I wanted to see, but no problem. We can validate through our console connection, and it's there, right there, D10-nano HPS test. It is created. Okay, from the NetBeans, it's just not available to browse through. Okay, so the next thing I want to do, instead of building the whole project, that will take longer, I will look for these. So in one of the videos I shared about or discussed about the multiple resources that I use and are available for the D10-nano development. One of them is the GitHub location, which is Zangman. It's named Zangman, and I think this individual who I don't think I saw the complete name of this individual, so I'm using this example, and it has definitely gave me a good direction. Although this goes through the whole portion of the SD card image creation all the way to the end, but I'm not following through those steps, so I'm just picking up the pieces where it applies to me. and right now the portion that we can use in our project is the C++ part where the HPS is going to write or read from the to or from the FPGA. So not the Linux driver, SDRAM communication, not the SDRAM controller. This is basically talking about the SDRAM, FPGA SDRAM is talking about a attachment that you can purchase for the D10-nano, and it's a separate card that has additional SDRAM on it. So this doesn't apply to us. What we will do, what we want is just write to the memory. And let me see. From the flash, I think the next few steps will take me there. Communication to the device tree configuration, design, somewhere in the design, I believe, somewhere here I did glanced over the C++ code. Yeah, there it is. So under the building SoC design, you will find the main code that you can modify for your application, and that's exactly what we will do as well. This is basically going to help us save time so we can continue our project and finish this quickly. Okay, going back to our memory location, which is basically lightweight memory, starts from the full chunk of the memory. The lightweight portion starts from the FF2 200,000, and for this example, the span, which is the portion that the memory we want to use, it's basically allocating 20,000. This is basically the address. It's not individual bits. It's the address of that span. Maybe I should say. Let me say it again. So this span basically is the additional address length. So if you add 20,000 to this 200,000, you will reach the address point in the memory where up to that portion the memory is going to be available for you to write. So yeah, we're going to use that. And lightweight mapping. Let's separate these out. Mapping and unmapping is being done here. So opening the memory, then map to the memory using that lightweight span, and lightweight base, that's our start memory address, and the okay, so let's continue. Okay folks, so here's our base memory, lightweight memory location, and this is the span. We can keep the span, we don't have to change it. However, if we want to change it, since it's just 4 bytes, our span, our memory span will be just the F. Or we can go one above that, 1F. So basically 4 bits and one next to that address. So basically, like, for example, this is a memory location 00000. We are occupying, we are saying that up to the first one or the next to the first one. Byte, basically, not the bits, the byte. So this is the F byte, and this is the next F byte. We're saying the first of that byte address, the second one, and the whole of the first byte address is going to be occupied. So, all right. So about 16 bits is what we are saying that we're going to occupy. Now from this, we will additionally, what we will do is we need a count. We need to count in 4 bits. So there is a unsigned integer 8 and unsigned integer uint. Let's see. Oh, uint 8, 64, 32, and uint itself. So we can just select uint. We don't need anything special. We can we do need the mapping, and we don't need the result, the blink times, we don't need that. LED mapping, we don't need that. Okay, so this will be our count, mtr count, and that's it. Just say 0. And what we will do is we do need the integer for the file number that we open. So this development memory, when it opens, its associated file number is going to be saved in devmem fd, and we can continue down to the mapping, which will map the lightweight base address using the span and 1F span, and we want to keep this lightweight mapping location, and from that location we will say custom LED 0 base. So custom LED 0 base is not created here for some reason. Okay, so we need that. Let's look at our example. The custom memory base, maybe I didn't copy the full program here. Ah, there it is. Custom memory base is basically 0. I'm pretty sure that it's going to be 0. Don't need to be any address. As you can see, that sets the custom LED map to the correct offset. So essentially, if you can imagine, when we map the entire lightweight memory, and we say, okay, the length of 15 bits is mapped to our program, then we have to individually, if we want to read the individual bits, we can say, okay, plus 1 bit plus 2 bits of offset. Basically, this is a offset from the initial address, the base address location, and that offset is then saved in another map. We can do that, or we can save it in the same map and continue on. In this case, it's saved in a different map, and let's keep that mapping. So I think I disabled that, so I'll keep that mapping. But I'll change the name. So this is not custom LED, this is the MTR count map. And the MTR count map will save this map location. The offset is 0. Do we have the offset? Same is not saved here. I can create one. This is the offset. Offset read memory location. All right, so that's now the reason why I want to keep this. What we can do is for the next one, when we want to write, this is, oh yeah, read. This is R map, read map, and this is write map. And we'll say, okay, write base. Maybe I should name it completely. Okay, the full name. That makes sense. So it's much better. All right, so let's rename it for proper. So we can see the full flow in our program without translating again and again for ourselves. So let's make sure that this is MTR count read base offset. Okay, goes here. Lightweight bridge mapping is going to keep the map. Offset from that point will be saved into the motor count. Motor count map, we have to increment that. So our custom LED is no longer valid. I'm going to change, pretty sure I changed the name up here already. So the custom LED map, here is it basically this is just turning on and off, and it's taking the pointer. Now remember, this is the address of that map, and if we want to save the value in that address, we have to call it as this asterisk and then the map location, and then we can say, okay, what we want to assign the value there, or which value we want to assign. In some cases, now in my example, I've used a notation to make sure that the format is saved properly, but I don't think we need to do that here. Okay, so I will save the count value, which is this guy. Motor count is going to be saved here. I think it wants to know the type. Make sure that if that's not correct, it is complaining about +1, I'll just do that here. Actually, let's do this. Less than 15. Motor count ++. And let's say now, why is this complaining about this? I'm going to make sure my format is correct. I don't think I need to specify the format like this, but so basically it'll count to 15 and then it will be done. I'm not putting it in a continuous forever loop. For now, I just want to count up to 15 and then be done. So if it hangs, it'll hang for 15 times 5 seconds. That will be that 25, 5, 6, 65 seconds. About 65 seconds, I'll have to wait about a minute, let's say, and then yeah, it'll be done. So it won't hang forever, at least. And then unmap the span, and then it'll close. Let's see if it's going to complain, what it's going to complain about. Let's see. I'm not going to. Cannot save. Why cannot save? Okay, hold on. I think there's a disconnect here. I'm going to save this somewhere else in a separate location. Oh, excuse me. And then I will try reconnect. Oh yeah, the connection was lost. And now the connection is back online. I'm going to save it again. Yeah, this time it's saved. Okay. Now we will compile. Let's see what it does. It's going to complain. It did complain. Yes, it did complain. Blink times. Oh, I didn't remove blink times. ATOI. I don't need the blink times anymore. I don't need to print that. And result. Yeah, result is, I think, a. Yeah, it's just a return status. Leave it in there. Something else. Offset is 0. Yes, it is 0. Or do I have to specify the type of the offset? Let's do that separately. Invalid operand. 32 unsigned int is used. But somewhere we're using more count, we are specifying motor count. Read map is 32-bit. We can make it smaller, we don't have to worry about. Okay, let's make it all the same. Do not use 32. 32-bit might be creating an issue for us. So let's see. Yeah, the offset still, it's still complaining about, it is offsetting for the void type, and we are not using the void type. When we come back and we do a read, motor count read, maybe the notation was not correct.